Welcome back. In this video segment, I'd like to discuss the effects of batch and setup on the capacity of a resource. So earlier on, we learned about the capacity, the meaning of capacity being the maximum speed, right, that the resource can execute, or in terms of a speedometer analogy, the maximum speed itself. So it's a constant, it's fixed, and it is also a manufacturing design. So it is built in, it is like the DNA of the resource. Now notice that I'm focusing on resource. The process capacity remains to be found out by getting the minimum resource capacity that is in the sequence of resources that form the process itself. So that part remains, as is intact. It's not going to be directly affected by what we're going to be talking about here. So the immediate effect of having batch and setup, all right, is to uh, reduce, all right, I want to say influence, but actually it won't go up. The purchased resource capacity is the maximum you can ever get, right? So if you bought a very expensive, high performance, high spec resource, whether it is a meat grinder, a packaging machine, a molding machine, whatever it is, the engineered processing speed, right, the maximum processing speed is going to be the capacity itself. So when there is batch and setup, right, what are the effects on capacity? And also, so I like you to pay attention to two process performance numbers. Capacity, that's something we keep talking about, right? In fact, the whole discussion of studying this operation topic in a very crude way is just to understand, right, capacity, this number. Of course, there are many things to worry about, right, in the actual factory and production process. But the important number, the key number, remains capacity. That means how capable are you? How fast are you in producing goods? Like I mentioned as an example last time, right? When, for example, Apple talks to its supplier Foxconn on producing, right, mass producing a new product, a new iPhone 27, right? So the first number is not how cheap or how expensive are you. First number that they should discuss is, can you produce the required 50 million sets per year? Do you have the capacity, right? So if our capacity is affected by batch and setup, then we might have overpromised Apple if we are Foxconn, right? And if we are Apple, because Apple will also send their very knowledgeable expert consultant to check, audit their suppliers, right? Not that the supplier intentionally lie, because if I know you're going to lie to me, I won't do business with you. But sometimes suppliers might screw up, might have accidents, might have overlooked, might have mistaken, might have miscommunicated, etc. So the Apple consultants will go inside the supplier Foxconn and check, right? Did you have batch and setup? Oh, you did, right? Oh, didn't you know that it has an effect? In other words, it tends to reduce your promised capacity, right? You cannot just read off the machine and say, oh, I bought this very high performance machine, so Apple, I can produce 50 million sets per year. When during the process of manufacturing, you practice batching and setup. Now we are going to have to suffer from this invisible side effect. And this effect is never good. It's always on reducing, all right, your actual performance, your actual capacity. So that's one. So that's one number I want you to keep track of when you know, look through all these terminologies here. And the other number is the flow time. Right? Flow time is, remember, the time for a particular marked flow unit, right? We put a star there, a sticker there, and watch it enter, and then we start the stopwatch. And when by the time it comes out from the process, we stop. And how long does it take for that particular flow unit to traverse through? So that's flow time. Now, what do batch and setup have in terms of the effects on the flow time of the process? All right, so you might have guessed it wouldn't tend to shorten it. It would only tend to increase it. All right, so these two things, batching and setting up, they tend to make things worse. Capacity, they tend to reduce it. Flow time, they tend to lengthen it. Remember flow time? The effects of flow time on the business? Why is longer flow time bad? Yes, right. If you recall Little's law, flow rate, assuming it's constant, not affected. But if flow time is lengthened, then what happens to the WIP, the inventory on the conveyor belt? FR times FT, right? So the amount of semi-completed goods, work in progress goods on the conveyor belt tend to increase, and that's cost, right? Because that's money locked up in the WIP that cannot be readily converted to cash, because who is going to buy over these semi-completed products? Not even your customer wants to buy, right? So don't even talk about competitors. So let's look at these two terms, batch and setup, right? And always keep in mind, why are we learning them? Why are we studying them? We want to know their effects on first capacity, very important, and then the effects on flow time, on our internal costs, right? The invisible internal costs. So what is batch, first of all? Just to have a common understanding, batch is just a group of flow units. And of course, we are talking about inside a process, meaning a process is a repeated cycle, like until infinity. So if you understand one cycle, one repetition, you basically understand the entire infinite cycles of process. That's at least is in theory. Yeah. So batch means that we're going to gather one group of flow units, right, and then process them before we go to the next batch, and then we process them before we go to the next batch, and we process them. So that's the kind of batch idea, collection idea. Yeah. Earlier on, we have been just thinking in a very straightforward, simplistic manner. The machine will mold one dough at a time. All right, the baking machine will bake one dough at a time. The packaging machine will take one baked dough, like almost a bread, and package it, right, and one bread at a time. In a batch scenario, we will have a tray of 4 breads, 4 doughs. So the molding machine will mold all 4, all right, one at a time, at least in terms of calculation. Okay, you might be thinking, okay, then that means one whole tray of 4 doughs, then the machine will move in the taking up the same time as if it is molding one dough, right? No, all right, no. So 4 times as long, 4 times as long. We don't have to worry about how the molding machine is conducted, whether it is a single mold with a robotic arm, right, with some camera vision or what, to locate the bread and then mold, then mold, right? We don't have to think of how it does it sequentially, or it has a 4-piece mold template, right? And then it just casts it onto the 4 doughs at once. But because it has to move very carefully, it's still taking up 4 times as long as it takes to mold a single dough. Okay, we don't have to worry about whether physically it's done sequentially, so times 4, or in parallel, but then 1 time of 4 takes up 4 times as long as the time it takes for molding one dough. All right, so we don't have to worry about the engineering design, just that time-wise, it takes up 4 times as long as it takes to mold one dough. Yeah, and so in a batch, if you have 10 doughs, then the molding machine will take 10 times as long to mold each of the dough in the batch. So once it finishes the tray, it ejects the tray, right? And then the baking machine will take in the whole tray of 4 doughs. And again, we don't have to worry about whether it bakes all four simultaneously, because that's very logical, right? We will think of that like an oven. Or it has only the size of one dough, and somehow the robotic arm will then do, you know, the internal taking in and taking out of the doughs into the one piece baking machine inside, right? We don't have to worry about how it's being designed or engineered. Okay, so it's 4 times as long as baking one dough. And same thing for the packaging machine. Okay, so that is the way you should be treating uh, the calculations in terms of timing. Yeah. So therefore, very importantly, you need to understand the definition here is this, right? No flow units can be taken out from the batch until all the flow units are processed. Very, very important idea. And the way to reinforce this in a very sort of non-negotiable way is to think of not a batch of not a tray of dough, because you might think that once you finish the dough, why can't you just take out the dough and then move on, right? Why must you wait for the rest of the three doughs to be molded, and then so it is very tempting to lead us in the wrong calculation. So let's think about the laundry. Yeah, so we have one basket, big basket of dirty laundry. You go to the washing machine and you shove all the dirty laundry into the barrel. So once it starts spinning and washing, you cannot say, hey, look, my t-shirt inside there seems to have been cleaned. Let me take that out, right? You cannot do that. It's not natural. It's not how we think about washing cycle, right? So that's exactly the idea of a batch in all cases, right? Even if you're tempted to say, but that dough is done, that bread is already baked. Why must I wait for the rest of the breads to be baked, right? Or that particular unit has been packaged. I can take it out and start selling, right? Why must I wait for the rest of the breads to be packaged before I take out the whole tray, right? No, it is as far as calculation is concerned, and the theory is concerned, a batch of dough is like a batch of dirty laundry. Once you put in the washing cycle, it starts, and you cannot take out anything, any shirt, even though it looks clean, but you cannot take out until the entire washing cycle for all the t-shirts and everything is done, and then you can open the door, right? That's our understanding. So please use that. Hmm. Another idea I want to give to you about batch is look around you in the classroom. Is the classroom a batch, or each each of you is flow unit, right? Each of you student is being processed, is being taught lean operations and analytics. But look at the classroom. Is this a batch? It is, right? It is a batch because one instruction from the instructor, everyone is being processed, right? Yeah. Whether it's one by one or um, done simultaneously is, again, as I keep stressing, is not so much the concern, right, in terms of calculation of time. But the idea of batch, this classroom, yes, is a batch. Classroom is a batch. Yeah. What happens if the class is not done as a batch, without a batch, without batching? Oh, well, then we have to then micro schedule, right? So student A, you come at 9 o'clock. Let me tutor you everything. Here's the cheat sheet. Do you have any questions? Let's finish up everything. You've got like 5 minutes. Okay, done. Next student, your time starts at 9:05. Let's do that. So we keep going. So everyone has 5 minutes, and we do that for 30 students. So 30 times 550 minutes. So that's about done, right? End of class. Can be done. Can be done. But and that is not quite acceptable, I guess, right? Nobody enjoys that. So as a class, that will be a batch concept. So in terms of this teaching mode, seems like batch is the natural thing. Okay, so that's why we have this concept, right? The batch. Now the batch size is just the number of flow units in a batch. So batch is a theoretic concept, right? Batch. Batch can be a tray, can be a basket of laundry, can be a class of students. Yeah. So the size is the corresponding number of flow units. So for the dough, I was saying four doughs on the tray, right? So that's batch size of 4. The dirty laundry, let's say 30 shirts, right? So then the batch size is 30. And then for class, maybe 25 students, then the batch size is 25. Okay, so that part is easy. But one more thing about this batch size. Remember, this batch thing is repeated in the process. So every batch is the same. So in a process, the batch size doesn't change from batch to batch. In real life, it may differ by 1 or 2, right? In a small quantity, just like class sizes. The same lean operations course might have 3 classes, but each class might have 25 students, 28 students, 34 students, right? So it may differ by some quantities. But in calculations and theory, we will assume batch size to be the same. Production cycle, repetition of the sequence of activities to produce units, right? So it includes setup time, production time, and idle time. So then we ask, what is setup time? Setup time is the setup time, right? It's the time taken to prepare, to set up things, ready for the batch. So very key idea to tie up these two is that whenever there is batch, there is setup time. And importantly, conversely, when there is no batch, at least theoretically, you cannot have a setup time. So now it's very one-to-one, okay? Very, very simple now, okay? So when there is batch, there is setup time means there is non-zero setup time. Don't tell me setup time equals to 0. That means there is no setup time, okay? So setup time equals to 0 means there is no setup time. So when there is batch, there will be some time needed to prepare for that batch, to receive the batch physically, right? So, and even electronically, even in software, we have to have a setup. It will be measured in microseconds, very, very short. But in terms of nanoseconds that the CPU is running at, it's still 1,000. Is it 1,000? Yeah, 1,000, right? 1,000 nanoseconds is a microsecond. So still very, very long time, right? Still very, very huge in quantity. So the setup time is still very substantial. So when is setup time substantial? When it is large relative to the processing time. So you don't want to compare with absolute like 1 millisecond only. What's so, serious, what's so severe about it, right? Compared to 1 second. But you are comparing with the wrong yardstick. You need to compare with processing time, P, processing time, the time taken to value add 1 flow unit. If the time taken to value add 1 flow unit, like the CPU takes, for example, for simplicity, okay, 1 nanosecond to process 1 instruction. At that rate, 1,000 nanosecond is a long, long time for the CPU to be sitting there. Are you done? Am I prepared? Am I prepared? Right. So it is relative to the processing time that we talk about. Right. So it is a severe setup time or not. So setup time is non-processing time. You cannot be touching the flow units. You are not value adding to the flow units. So what is setup time? What do you do it for? You do it to for example, change over, to get ready for the next batch, to get ready for a new model, to get ready for the next batch in terms of maybe the mechanical arms and all that got to be reset at a standard position. The overheated processing engine or whatnot got to rest a little bit to cool down, right? Because if you keep running, it may overrun, right? So due to safety, due to um, optimal operating conditions, it is required by software or by operating manual to rest a bit. So the setup time, even though we say set up, sounds like at the start of the batch, right? So you prepare to receive the batch. This setup time also includes the intermittent mandatory rest in the middle. So for example, our class, right? When I come in, I may need 5 minutes to, clean the table, lay out my stuff, right? Then power on the projector, wait for the screen to come down. All these might be just 3 minutes, right? 4 minutes. Still, it is setup time, non-zero, isn't it? Yeah, because I'm getting ready to for the class, and sometimes it's not just me. I take three minutes, 4 minutes, and then I look around the class, half empty or half full. So no choice. I gotta wait a little bit more, another 6 more minutes for the rest of the students to come in. All right. So it's like no choice. My CPU cannot start, right, until my flow units are done in the batch, right? So until the batch is filled, then I can start. Otherwise, I start halfway through, all the students will be asking the same questions. What do you cover at the start? What is batch? So because now you see, right? Now it's not just because of the resource itself, but it can also be the way the flow units are being conveyed, the way the batch is being formed, and various other situational kind of factors. So depending on what you are talking about, what flow units, what factory, and so on. So setup time can be at the start, in the middle, or at the end. For example, some processing might have to clean up, right? To not clean up whatever has been the debris or the leftover, or the dirty floor, so that you can get ready for the next batch. Okay. If you consider a batch of one flow unit, then you can think about the hairstylist, right? So if you are going in, the hairstylist will, okay, cut your hair, wash your hair, whatever it is, wash first or cut first, I don't know, and then color your hair and whatnot. And once you're done, the floor will be dirty, right? So he or she cannot immediately receive the next guest or customer, right? Instead, he will have to sweep the floor first, clean the hair on the floor, clean it up, make sure it's a nice environment, everything reset, and then you're ready, right? So that is the cleaning up is the set down time, whereas the dusting of the table and whatnot, you can consider set down, you can consider set up for the next cycle. Yeah, but whatever it is, setup time can be anywhere in the production cycle. That's what I'm talking about, right? So just be on the lookout for that. Now, also another example, I was talking about the 5 minutes and 10 minutes of setup time I have, and in the middle of the 3 hour class, we have to have a break, right or not, right? Otherwise, our brain cannot handle. It's not overheating, it's just drowning, right, in over information, right? Overloading. And so we have to have a mandatory, let's say, 15 minutes rest time. So that's considered setup. Yeah, okay, yeah, because that's going to reduce the time uh, available for processing you, for uh, of course giving you knowledge, but also receiving questions from you, probing your understanding and various class exercises, right? And whatever it is, having a rest break is not wasting time because we need that, but then it is also reducing the time available for further learning on this topic, right? Yeah, so now you can understand. So setup time is, although non-processing time, it is like super needed, isn't it? Yeah, it is also important, though it's not value adding. So just understand this part. What is the effect of setup time? The effect of setup time is to cause the resource capacity to be lowered. Okay, let me say again. The presence of setup time, the longer the setup time, the resource capacity, the effective resource capacity becomes lower. The longer the setup time, the lower it is. The effective, not the peak performance, the peak capacity. I call that the machine label capacity. So when you bought the machine, okay, the machine can handle 6 flow units per minute, the packaging machine. But with setup time, okay, you have a company policy that says before processing each batch, the supervisor must first look around the table, right? Clean up the desk, must make sure you eyeball and check, yeah, the safety latch and something like that, right? Safety procedure. So all these take 10 minutes less. Okay. So within an hour, you need to have 10 minutes to do all this inspection. Then you process a tray, right? A tray of 4 doughs. So this 4 doughs, right, will take no time, very quickly, because it will take 40 seconds, yeah, to finish. So the 10 minutes is like within the 10 minutes you can do a lot already, right? But because of I'm exaggerating the 10 minutes setup time, but if it takes 10 minutes to set up per batch of dough for packaging, then you can imagine how much time is so-called wasted in having this setup time, right now, yeah. But then from as far as the company is concerned, from the company's perspective, it is not wasted. You better be operating in a safe environment. So please check this, check that, right? You don't check, then that's when accident happens. So again, you say setup time is wasting time. No, it is very important. But are you value adding to the dough, the flow units? No, right? So it's like no choice. So a super duper high performance, high resource capacity packaging machine, 6 per minute, end up delivering only maybe 1 piece per minute kind of effective uh, capacity. Okay, so the 1 per minute, I'm just roughly guessing. I'm just trying to show you how drastic that be from 6 all the way down to 1. You only enjoy 1 per minute because of your very severe setup time needed. Okay, so I'm not saying because of this bad thing, setup time is bad. I'm saying we need to be aware because we have found good reasons, right, in having the setup time per batch. But because of that, the presence of setup time, the non-zero-ness of the setup time always reduces the effective capacity. So just on the watch out for that. Okay. So each time a new batch is processed, setup time is incurred. And then in the middle, setup time may additionally be incurred. Towards the end, cleanup time is also considered the setup time for this batch, also incurred. Okay, so let's look at the picture here. Yeah. So this is the time axis. This is the time axis. We have an example of, let's say, a batch size of 4. Setup time is 2 minutes. Processing time is 1 minute per flow unit. So let's say it's making the bread, right? So a tray of 4 breads or 4 doughs. Setup time 2 minutes for the machine to self-check, analyze this and that, and for the operator to also check, inspect, and then processing. Yeah, so the processing, the baking, let's say, of each dough is 1 minute per bread. So the resource capacity 1 per minute. 1 per minute. So the C is 1 per minute. Let me call it CML. So the capacity for machine label. The machine says this baking machine is 1 per minute. So if we don't have batch and don't have setup, then we are just having 1 per minute, and that's the maximum it can go right now. Yeah, very fast, right? But let's say that we are now and the machine is capable of doing a tray of 4 at one go. But because it's a tray, the machine takes additional 2 minutes to align the tray and whatnot. So you can understand. Now let's look at the time axis. In the first tray processing, the machine incurs 2 minutes, right? Then it starts to bake and bake and bake and bake, 4 of them. So 4 minutes. Yeah. So altogether 6 minutes. You can follow. Yeah. So after that, because this runtime is the pure processing of the batch. So it's P times B. P times B. So P times 4. So 4 times 1, that's 4 minutes. S is the singular setup time, so 2 minutes. And the operation time is basically the everything added together, setup time and the batch runtime. Yeah. And then we repeat, right? So it's repeated cycle like that. And for simplicity, let's do it 3 times only, not infinite number of times. So after 3 cycles, let's do the math. We would have waited 18 minutes, correct or not? Yeah, because each operation time is 6 minutes. 6 times 3, 18. How many do we get? How many baked doughs do we get? 12. So the net capacity we get is 12 divided by 18. That's 0.6667, not 1. What did we say at the start? The machine is capable of a resource capacity of 1 per minute, right? That is slow. But with the presence of setup time and batching, it is even slower, right? It's like having a 30% discount of the purchased resource capacity. Now, what if there isn't any batching and setup time? So the usual way of processing. So 18 minutes, we would have gotten 18 flow units. So 18 over 18, 1 per minute. That much is easy to understand. So comparing these two, you can see that the presence of setup time only serves to decrease the effective capacity. I call this the CBS, capacity in the presence of batch and setup. Whereas this this original resource capacity, I don't want to call it original. It sounds like we are faking or we are what. So machine label, the original machine label. I bought this machine which is labeled with or engineered with a capacity of 1 per minute. So that's the effective capacity back to the machine label capacity. That's the best we can hope for. Well, that's the maximum. Okay. And the bottom diagram is to give you a sense of batching, right? Increasing the batch size without increasing the flow rate. So now we try to look at batch size and flow rate. It might sound as if when we increase the batch size, like double the batch size, so one tray, right? Every tray, 1 tray per minute, each tray having 1 flow unit, the effective flow rate is 1 per minute right now, yeah, because you just throw away the tray and basically it's 1 per minute. If we double, all right, the number of flow units per tray, if we don't draw the picture, we would imagine, wow, in 6 minutes time, there would be 6 times 2, 12 flow units being sent in, right? So 12 divided by 6, 2 per minute, right? So if we double the batch size, we would double the flow rate, right? Like we are feeding double as fast. But no, we can still maintain the flow rate by like skipping 1 tray every 2 minutes, correct or not? Yeah. So if we have 1 tray every 2 minutes, and each tray has 2 flow units, then we are still maintaining a flow rate of 1 per minute, like this. So the distribution, if you plot the statistics, after 100 minutes, we would see 50 trays of having no flow units, no tray, due to no tray, and 50 flow units due to 25 trays, something like that, right? So if you average these two, 0 times 50 plus 2 times 50, you will end up getting 1. That's the expected value of flow rate. Expected value of flow rate is 1. So going by that analogy, we can halve it some more and double the batch size some more, right? And you can imagine that what's the flow rate? Same. I'm dropping the frequency of supply of the trays. The frequency is halved, but the tray size has double the flow units than before. So we have 4 per tray, but each tray is sent in every 4 minutes. And then of course you can do the math, right? So it's like 0, I see 75% of the time. Every 4 minutes, I see 3 zeros, and every 4 minutes, I see 1 tray of 4 flow units. So the 4 flow units, I see 25% of the time. Again, if you do the sum product of 0 to 75%, 4 and 25%, you get 1. So that's to illustrate to you that we have a way to maintain flow rate as we increase or decrease the batch size. Okay, yeah, of course, I am showing the easy numbers. So sometimes we may not be able to maintain exactly at 1.2355 per minute. Yeah, because then you got to shift the trays very exactly, but then it's a conveyor belt discrete segments of positioning the trays, so you cannot shift the trays arbitrarily, right? So end up, yeah, your flow rate in actual fact does fluctuate a little bit. But I'm just trying to say that theoretically it's possible to maintain. So don't get the wrong impression that every time you double the batch size, the flow rate will increase. Oh, then we'll be in trouble. So don't worry about it. Okay, next. Just want to have a final slide to round up this understanding, right? Because some of these terms we have already mentioned, like CML. Out of no choice, I have to invent this term, right? Called CML, which is the machine label, which is the C, which is the capacity that we talked about, the resource capacity. Okay. And then the processing time is always 1 over CML. Here is the potentially confusing part. It's always 1 over CML, not 1 over CBS. So in other words, you don't go and calculate the effective capacity in the presence of batch and setup time, and then use that to take the reciprocal, like 1 over CBS here, then you go and calculate P. It will be all wrong because P is needed inside CBS, right? Not so you need to be very clear. P is strictly forever in DNA down to the last atom tied to the CML. Cannot change this, right? So always true, and it's the reciprocal of CML. Reciprocal of CBS, no term for that. Okay, so what is CBS? That means the effective capacity in the presence of batch and setup time. The word definition is kind of most useful, like what we did just now. After some total time of measurement, we count how many units we actually get out of it. Total units over total time taken. So if you do this ratio, it is always correct. Then we have formulas, but these formulas are only applicable, right, when you make certain assumptions. But this one, total units process, you can have arbitrary any mix and match. Like setup time is 1 minute for the first tray, 2 minutes for the second tray, 3 minutes for the third tray, and then back to 2, back to 1. You can do all these funny things. The numbers, instead of being constants, can start to change from tray to tray, from batch to batch, and then you still can use this word formula. Total units after total time. Of course, you choose a convenient total time so that you have integer units being processed. So don't like cut halfway where you get a quarter or half a flow unit, right? Then it becomes very hard. Okay, but then these are also useful, the formula, because when they make suitable assumptions, right, such as there is constant batch size and constant setup time, then you have this B over S plus PB, correct? S plus PB is the total operation time in one cycle, let's say, right? We get B units. So what's the effective capacity? B over S plus PB. The note here is that if the prevailing flow rate is not stated, then we assume that the prevailing flow rate, right, the flow rate, which is less than CML, remember in previous discussion, we assume it to be CBS. That means the maximum we can go in the presence of batch and setup time. You cannot go above CBS. You cannot. Just cannot. Your CML is 1, your CBS is 0.67. You cannot flow more than that through this resource. All these discussion is about resource. CML is defined for only a resource. Okay? But then, of course, you ask, what about process capacity? Yes, process capacity is affected by batch and setup only when the bottleneck is affected by the batch and setup. Okay, or when other non-bottleneck resources they are affected by batch and setup so severely that they become bottleneck, and then they become the new process capacity. In other words, for the process capacity, you basically look at all the CBSs, all right, all the CBSs for the various resources and find the minimum. So the calculation is still the same. The calculation is still the same. Yeah. So for example, if it is possible, right, if a particular process is such that um, molding, baking, and packaging. Remember our three-stage bread making factory, right? Um, baking was the bottleneck, right, at 1 per minute, and molding was not too far away, 2 per minute. So have if we change the molding machine to a batch molding machine, and the setup time is so severe that the molding machine now becomes 0.8 per minute, and the baking is not, it's still singular, right, and the packaging is still not. Now the overall process capacity becomes the minimum of 0.8, 1, and 6. And yes, then the process capacity is being altered, being reduced. But then if the molding has a batch mold, all right, maximum 4, for example, but the setup time is 30 seconds or whatnot, in such a way that the 2 per minute the CML is 2 per minute for molding machine gets reduced to 1.6 per minute. It is a very severe reduction. But then in the overall scheme of things, the minimum of 1.6 and the baking machine's 1 and the packaging machine's 6 is still baking machine. So process capacity, no change. Excellent. Right? So you will have to recompute. But then the formula for recomputing the process capacity, even in the presence of different setup time and batch sizes for different resources, is still the min of everything. It doesn't change, right? Okay. Runtime, operation time, I have illustrated that. And then I want to steer your attention to the right two graphs. Of course, graphs are easier to understand. And let me move myself away from that. So graphs are easier to understand than words. The two graphs here are basically trying to talk about the shape of this function in terms of B. B is the batch size. Batch size. Yeah. As batch size gets larger and larger, okay, so as B becomes larger and larger, and we assume S is constant, setup time is 10 minutes fixed, right? But if setup time is fixed, our batch size is larger and larger. You can think of S as the fixed cost, and P is the variable cost in terms of time. So we are going to, no matter what, spend the fixed cost S minutes, the fixed cost in terms of minutes, not dollars, but minutes. So we have to spend S. Whether we use 1 per batch or 10 per batch, we will still have to spend the fixed cost. And then as your batch size increases, your total runtime increases. P times P will increase, right? So P is fixed, variable, more flow units in the batch, larger runtime. Yeah? So how will the effective capacity, CBS, behave? It will behave like this. As B approaches infinity, we are going to recover back our lost glory, right? Our CML, the very top maximum maximum capacity. So CML is the highest capacity we can ever hope to get, right? And if we have a very severe, very, very large fixed cost, as it makes sense to have larger B, because the initial increase in B is going to have a very huge effect initially. After that, there'll be like the point of diminishing return. Let's say after 20 in a per tray, if your molding machine can take that, after 20, 20 to 21, 22, 23, marginal increase. right? But then initially from 1 to 2, it's like 2 times the increase from the original CPS, like double, you know. So it makes sense to maybe quickly increase to 4 or 8, something like that. So if you see this, then we know what to do. Okay. Next, if we have a fixed batch size, all right, fixed batch size, we hold it constant, so we can cancel out actually. And as the setup time increases, what happens to our effective capacity CBS, right? So as S increases and the rest are all constants, then basically we are having 1 over infinity, right? Right. So because this even if it's very large, 100 minutes, eventually when S becomes 1,000, 10,000 minutes, it will sum out the PB. PB becomes like round off already, right? So basically 1 over infinity, and CBS goes to 0. So as S increases, it goes to 0. So almost like a reciprocal relationship. I want you to be putting attention here, right? It's like having the opposite effect of B. When we, because of this curve being the same for all kinds of machines, resource, man-machine work team or whatnot, right? It makes sense to increase B initially, all right? But it doesn't make sense. It'll be point of diminishing return when B is already very large. The reverse is kind of true here. When you somehow have the need to increase a little bit of the setup time, right? From no setup time to little bit more setup time, the drop is very severe. The penalty, right, or the loss in capacity effectively is very, very severe. So from 0 to 1 minute is very big amount of discount, like 30% discount. From 1 minute to 2 minute, it's like a 50, 55, 60% discount, like 50% discount. From 2 minutes to 3 minutes, it's a 60%. So the additional penalty is like 10%. Additional penalty 5%. Then it's like diminishing penalty. So after a large enough setup time, like 20 minutes relative to a processing time of 1 minute, you want to increase 20 minutes to 25 minutes, go ahead. I mean, it's not going to reduce much. I'm already very severely penalized with you, right? So, but then watch out, huh? You might just end up not doing anything productive. So the lesson learned here is that be very, very careful. When you have no setup time, you end up having to force yourself into having a setup time. When I say having to force yourself means, for example, there is a safety check. All right, now we can debate about it, whether it's necessary or not. But I'm just saying, when the company is very, very worried, right? Why are you worried? So worry is something that is very hard to justify. It could be real worried, it can be imaginary fear, right? So you just want to revisit this again because there's a very severe pain initially. And that means, like, if your CML was bought with $1 million because of the high capacity performance, a bit of increase in setup time is going to cut your investment as if you have bought a 500,000 machine, isn't it? That's a huge loss. And you and it's self-inflicted, right? If it is company policy, if it is mandatory for the worker to exercise, dance a little bit to loosen up your hands so that you are more alert, to keep your blood cycle circulation going, so that you are more alert and you are less prone to accidentally cut your fingers or whatnot, right? And then be willing to revisit this again and see whether you really want to do this or not. So that's what we are learning here. Choosing the batch size, right? So like we say, large batch sizes will end up extending the flow time. Why? Because all the items, you have very huge number in the tray, and all the items cannot be taken out until everything is done. Correct or not? Yeah. Think of laundry machine. Think of the class, right? If you are done with your questioning, if you understood everything about today's batch and setup, can you leave the class now sorry, I think you won't be so discourteous to just stand up and go, right? You might still want to sit through and hear any exam tips, right? That is usually given out at the end, maybe. So uh, the total flow time becomes longer, right? And when the total flow time becomes longer, using quickly applying Little's law, flow rate is the same, flow time is larger, the WIP will be larger. So from business school's perspective, large WIP is always a bad thing. And if the process is capacity constrained, all right, capacity constraint means people want our products, but we cannot produce fast enough. So we are constrained by our capacity. And the setup time occurs at the bottleneck. That means the bottleneck is already a bottleneck. And the setup time, that means severe setup time, when we say the setup time, right? And the setup time, the severe setup time is observed at the bottleneck. Then, and yet, setup time cannot be arbitrarily decreased easily. Not very difficult, huh? Very difficult. Therefore, increasing the batch size will increase the flow rate. And that's true, right? If the process is demand constrained, the other way around, we can produce, but nobody wants our bread. That's a very nice way of saying your product sucks, right? Yeah, so nobody wants, and it is a very nice way to say demand constraint. So next time, if you have a friend who drew a lot of what he thinks as a very beautiful art, right, and he keeps saying nobody wants to buy my art, right? Then you can just very courteously say, I agree, it's quite demand constrained. It sounds very nice, huh? Or, okay, the setup occurs at a non-bottleneck. So let's look at it one at a time. Demand constraint, we can produce, nobody wants. Then decreasing the batch size will decrease the inventory as well as flow time, as well as um, our production, right? So our output will reduce, and supply that initially was oversupplying, nobody wants, right? So the FR demand was low, our FR out was high. Reducing batch size will serve the effect of reducing the FR out and thereby regaining, hopefully regaining the supply equals to demand situation. The other situation, setup time, severe setup time occurs at a non-bottleneck. Non-bottleneck. Even though it's very severe, like just now I was saying, right? Molding machine, twice the capacity of baking machine. Baking machine is 1 per minute bottleneck. But then severe setup time, right? So a 1 minute setup time, because it's compared to 2 per minute, it's very severe. Severe setup time occurs at a non-bottleneck, occurs at a molding machine, right? Then decreasing the batch size will decrease the inventory as well as flow time. So you can then decrease the batch size, right, which will decrease the inventory as well as the flow time. That's what it's trying to say. All these are actually cause and effect due to Little's law, due to the way we define the batch and setup time, right? Because setup time is incurred for every batch. That's why all these things automatically occur. Okay. Now, so this is the last slide, but I just want to add one more note about the ease of control between setup and batch. So here we keep talking about choosing batch size as if we can change it very easily. And it's true, right? If you think about the tray of dough, if the molding, baking, and packaging machines can process a tray as well as singular dough pieces, then you can imagine that we just put one dough in a tray or 4 doughs in a tray, right? Maximally, let's say, quite easily. We just choose. We just select. Even Monday, Tuesday, Wednesday can have different batch sizes. Correct or not? Yeah. So if we are selling to retail customers, we know that the Monday's traffic and the Friday's traffic and the Wednesday traffic, they are different. So we can then easily change our batch sizes to influence our FR out so as to meet the FR demand, right? So we don't exceed or we don't go under the FR demand. And that's very easy, almost cost-free. But changing setup time, and of course when we say changing, we don't want to say increase purposely, right? So whenever we say changing setup time, it's always meant to say reducing setup time. So reducing setup time, can it be done? Yes, but very reluctantly, huh? Because high cost, number one. What is the meaning of reducing setup time for the molding machine? This molding machine comes with a pre-programmed, pre-engineered tray processing internal software. You cannot change it. You cannot reduce the setup time. It has this self-diagnostic that takes 30 seconds. You cannot reduce to 1 second. Cannot, right? So the only way that we, the business owner of this molding machine made by another manufacturer, is to change the machine, upgrade, right? So now you can imagine, to buy a better molding machine. Better means higher or lower setup time? Of course, lower, right? Yeah, because lower setup time, higher performance, higher net performance. So when we buy another machine that boasts lower setup time, same CML, same processing per unit, but lower setup time, do you think the manufacturer will sell higher or lower? Of course, that manufacturer is not totally ignorant of the market rate, right? Yeah, so they know they engineer this to have lower setup time because they know it's a better product. So they're going to charge you higher. So you're going to spend more money. That's number one. Do you have the money? Now, if you're selling to retail like those Heartland Mall, small bakery stores, a bit tough, right? A bit tough. So that's number one. And even if you find the funding to upgrade the machine, there's a downtime needed. Now imagine that 24/7 you're selling, huh? You're selling and selling and selling. Now you have the money to buy the new, better molding machine with a lot of reduction in setup time. You got to switch off your molding machine. But that means switching off the entire production line. That means switching off your money income, right? Your profit income. So no choice. It's very expensive. And if the installation, the changeover time is long, 7 days, hopefully it's 1 day. But if it's 7 days, and usually it's not a 1 day affair because you got to sight the machine, or you got to the incoming machine might be bigger, right? Might be hotter, so you need some more air gap. Might require a bit of fan space, or whatever it is, right? You can imagine. So the requirements may be slightly different. You have to sight it. And once you put it in, you've got to connect here, connect there, sometimes apply for permit that has to wait for another 2-3 days. For Singapore, it's already very fast, and imagine for other countries. So 7 days. After 7 days, you have lost a lot of money, right? Basically, you say, our shop is closed for upgrading. Please come back after 7 days. And you risk losing customers because they are forced to go across the street and they discover a new shop that sells better cakes and bakeries and new tastes and everything, right? And will they come back? I'm sorry, right? I'm not too sure. So the number three is the risk of losing customer, right? So a lot of consideration when you say reduce setup time. But is it right in this course to say reduce setup time? Absolutely. So during exam, please remember to say the company can attempt to reduce setup time. How? Don't say, right? How? You are unable to suggest unless you know more details about the company. Because even if they are saying, even if the exam question is saying, you are the consultant to John the bakery store, suggest ways that he can increase his productivity and all that. Oh, John should consider reducing setup time, right? How to reduce? Don't even open your mouth because you don't know much detail, right? Like what machine is he using and all that stuff, and all the sighting details and all the training, the maintenance required. Don't know. So very, very difficult. So usually it's a business consultant that comes in, right? So yeah, expensive stuff. But is the idea right? Idea is right. So always remember to suggest reducing setup time. It's a constant battle, but it's the right battle. Okay, thank you. See you in the next video.